So in example 6 here, this is really referring back to example 5. It's the same experiment and the same events. We've got, we're going to roll 2 dice, red and blue. We're going to define the events. A is the event that the red die is 3. B is the event that the total is 7. C is the event that the total is 8. So we saw those before. We calculated the probabilities of each one. And in fact, let me go ahead and remind you what they were. And if you don't remember how we got them, or if you haven't just looked at example 5, go back and check through example 5 and you'll see where all of these come from. The probability of A was 1/6. The probability of B was also 1/6. And the probability of C is 5 out of 36. And then we also calculated several conditional probabilities that are going to be useful here when we're determining independence. I'll just write down some of the useful ones here. The probability of A given B, we calculated this last time, well, in the last example, in example 5, turned out to be 1/6. The probability of A given C, I'm skipping ahead to the ones we're actually going to be using. Probability of A given C turned out to be 1/5. And the probability of B given C, because those were disjoint events, it turned out to be 0 because they can't both happen at the same time. So now we're being asked, are events A and B independent? What about A and C? And what about B and C? So for A and B, remember independence, by definition, it means the probability of A is equal to the probability of A given B. Intuitively, it means that if you calculate the probability of A with no information, or if you calculate the probability of A with the information that B is true, you get the same answers either way. So let's just check those out. Probability of A, I wrote down, was 1/6. Probability of A given B is 1/6. Those are equal. So that tells us that, yes, A and B are independent. Are independent. That's our answer for A and B. Let's look at some of the others. What about A and C? We're going to look at A and C. So let's calculate the probability of A, and we'll check whether it's equal to the probability of A given C. So the probability of A is 1/6. Got that up above. Is that equal to the probability of A given C, 1/5? No, that's not equal. 1/6 is not equal to 1/5. So that tells us that A and C are not independent, they are dependent. I'll try to give you some intuitive feel for that in a moment. I want to go through and do all the calculations first. Then we'll come back and see if we can make some kind of intuitive interpretation of this. So that was for A and C. Now B and C. Sort of tempting to say they're independent, because if you're thinking like some students think, you say, oh, total is 7, total is 8, those can't both happen. You might think, oh, that means independent. That does not mean independent. That means disjoint. So let's actually calculate it using the probabilities. Is the probability of B equal to the probability of B given C? That's our formal definition of independence. So let's check and see if those are equal. Probability of B is 1/6. Is that equal to the probability of B given C is 0? Is 1/6 equal to 0? No, it's not equal to 0. So that tells us that B and C are not independent, they are dependent. Now, we did that all using calculations, using the calculations that we got from example 5. So if you don't remember where these numbers came from, just go back and watch example 5, the one just before this one, and you'll see where I got all these numbers, the 1/6, 1/6, and 5/36 for A, B, and C. And then we calculated the conditional probabilities, 1/6, 1/5, and 0. We calculated some others in example 5, but I just extracted the ones I would need here. Now to check independence using calculations, you just check whether the conditional probability is equal to the probability without making the assumption that the other event is true. So that's what I checked. I just checked the numbers each time, and if they were equal, I said they're independent. If they're not equal, I said they're dependent. So that kind of answers the problem, but it would be nice to have some intuitive reason for why these might be true. For A and B, it's not so obvious. If the red die is 7, why is that if the red die is 3, what does that tell you about the total being 7? And the answer is it doesn't really tell you anything, because the total being 7 was a 1/6 chance anyway. If the red die is 3, then I know to get the total being 7, I need the blue die to be a 4. And there's a 1/6 chance of that. So telling me that the red die is 3 gives me no new information about whether the total is 7. That's why A and B are independent. How about A and C? The red die is 3 and the total is 8. You might think that that's similar to the previous one, to the red die is 3 and the total is 7. But it's not, and here's why. To get the total being 8, let's think about how that can happen. How can the total be 8? Well, you can get a 2/6, you can get a 3/5, you can get a 4/4. These are all ways to get the total being 8. You can get a 5/3, or you can get a 6/2. In particular, for the total to be 8, you can't roll a 1 on either die. So if I tell you that the red die is 3, if I tell you that A is true, if I tell you that the red die is 3, what I've really told you is, in particular, that the red die is not a 1. That makes it slightly more likely for the total to be 8, because we know now that the red die is not a 1. That's why P of A given C is slightly higher than P of A alone. So if I guess actually that means I've told you that the total is 8. That means that the red die cannot be 1, which makes it slightly more likely for it to be 3. That's why we get a 1/5 over here and a 1/6 over there. I'm giving you a little bit of information when I tell you that the total is 8. I'm really telling you that the red die can't be 1, which makes it slightly more likely for it to be 3. Now B and C is easier to understand intuitively. If I tell you that the total is 8, I've given you some information about whether the total is 7. I've told you that the total is not 7. So I've really changed the probability on you. As soon as I tell you that the total is 8, you know for sure that the probability is not 7. I've really changed your thinking. And so those are really dependent events. They do affect each other. So that's kind of an intuitive reason why we got these answers that we did. Why A and C are dependent, B and C are dependent, but A and B are independent. So there's a lot of twists and turns in conditional probability and independence. I hope you all have fun playing with those. We're going to move on to the next lesson, but I want to say thank you for joining us today for the probability lectures on Educator.com. My name is Will Murray. Thanks for joining. Bye-bye.